Alright, we're in section 3.9. It's the end of chapter 3 for us. So it's called implicit and related rates. The book might just call it related rates. We'll talk about in a second why I'm calling it implicit differentiation related rates. There's only one thing to do, and that's to solve related rates problems. Related rates problems. So, what our little paragraph, our box here is saying is sometimes both variables in an equation, they are implicit functions, which is one of the reasons I'm saying this section should really be called implicit differentiation and related rates. So because they're implicit functions, they're usually implicit functions of the same independent variable. A lot of times it's t for time, so you have two things that change over time. Quick little example here, the price P for weekly sales X of some good or commodity could be related by a demand equation where both price and quantity depend on, the month, the time of year. You differentiate both sides of that equation in the demand function with respect to time. You use the chain rule so that you end up with two derivatives in your final answer. You'll have a dp dt or a p prime, and you'll have a dx dt or an x prime. So these types of problems are all relating two things to one another, hence why I have here it's relative, why we call them related rates problems, because the rate of your two variables or your two implicit functions, they are related to one another, either through an equation or through circumstance. So we just have three problems here in this chapter, or in this section, to walk through to kind of show. So this first one is a pretty classic related rates problem. So it says a pebble thrown into a pond causes circular ripples to radiate outward if the radius of the outer ripple is growing by 2 feet per second. How fast is the area of its circle growing at the moment when the radius is 10 feet? So there's a couple things you want to be doing when you're tackling related rates problems. So number one is identify the known and unknown rates, comma, variables. So we know we have radius, which has a rate. We know we have area, and we know we want the speed of the area. And we also know the radius at a moment, at a specific time. So I know I have an A, I have an R. I know my rate, dr dt, the change of the radius over time, is a positive 2 feet per second. I know the radius at the time in question is 10 feet. And dA dt, the rate of change or how fast the area is changing, that's the unknown. That's what I want to find. So what we need to do is relate A and R, dA dt and dr dt, with an equation. So since this is circular, we're going to use, number two here is to identify the relation, which is just an equation. So for our case, this is A equals pi r squared. That's what relates area and radius of a circle. So part 3 is then to implicitly differentiate So this would be A prime, derivative of A is A prime because A changes with respect to t, equals 2 pi r prime, because r changes with respect to time. And then we plug in our values. So we're looking for A prime. We have 2 pi. At this particular moment we care about, r is the 10 feet. R prime is dr dt, which is 2. So this is going to be 40 feet squared per second. That's our final answer. That's how fast the radius is, or the area is increasing when the radius is 10 feet. That's the basic principles of these related rates problems. So the majority of the work comes in correctly identifying all of your stuff and then making sure you have the right relation. And you want to make sure that you are not choosing something that has more than one variable in it. Because let's say we chose, I don't know, circles are a bad example for that, but something like surface area. Surface area of like a cylinder is based on the radius of the circle base and the height of that cylinder. So you have your circle and your height. That would be a bad choice unless you know something about the height or the radius specifically. So you want to try and keep it to one variable. So let's try out the next one here. A boatyard's total profit from selling X outboard motors is negative X squared plus 1000 X minus 2000. If the outboards are selling at the rate of 20 per week, how fast is the profit changing when 400 motors have been sold? So we know we've actually already been given the variables P and X. And we know dx dt, this changes week to week because right now we're selling 20 per week motors per week. Motors. And we know we want dp dt because it asks for how fast the profit is changing, so that's going to be our question mark. And we know the X value that we're worrying about is 400 motors. So they gave us the relation. Excuse me. They gave us the relation. So sometimes some problems will give you the relation if it's a custom thing. So this is custom to this problem. Sometimes, like in this first example, you'd be expected to know what the radius of a circle is, or the area of a circle is. So we need take our derivative, dp dt, be negative 2x dx dt plus 1000 dx dt, and derivative of 2000 is 0. So in all of these related rates problems, every single variable that has a ddt that we've created here needs to be implicitly differentiated. And when you just have your variable like p, well, the derivative is just dp dt or p prime. So I'm showing you both ways that we can write this. Here I wrote it as a prime. I could have written this as dA dt. Here I'm writing it as dp dt. I could have written this as p prime. dx dt could be x prime, just like r prime here could have been dr dt. So now we plug in what we know. We don't know dp dt. We know the x that we care about at the moment is 400. dx dt is 20. Plug in dx dt again is 20. So this is negative 16,000 plus 20,000. So that's 4,000, which means dp dt is 4,000. P is profit, so this is dollars. And this would be per motor sold. Because our function was all about X, which is the number of motors that are being sold. So those are two basic examples here. Let's flip the page here and look at a couple more well, it's one example. We're doing 3 different problems with it. And it's a little bit more interesting because of that. So we have loose landscaping, and their total revenue from yard maintenance of X homes is given by R of X is 1000X minus X squared. The total cost is given by C of X, which is 3000 plus 20X. And suppose that loose is adding 10 homes per day at the moment the 400th customer is signed up. So at that moment, what is the rate of change? And we're going to do 3 parts: the total revenue, total cost, and total profit. So there's a couple things that are going to be true for all 3 of the parts. For one, the rate of change of the number of homes, dx dt, these are all going to be the same moment. So dx dt, they told us, was adding 10 homes per day. So that's 10, positive 10 homes per day. And we're looking specifically at the moment where there's 400 homes. So in part A, we are trying to find dr dt. That's what we want. So we're going to take the derivative of r of x, r prime of x. But we're not doing r prime of x, so scratch that. We want dr dt, which treats r as a function of t and x as a function of t. So we take our derivative, 1000 dx dt minus 2x dx dt. Now that we have this, we plug in our values that we know. So dr dt would be 1000 times 10 minus 2 times 400 times 10. Should be 10,000 minus 8,000, or 2,000. And since this is revenue, dr dt is $2,000. And this would be per home. So box that up. Part B now says do the same thing, but we don't want dr dt, we want dc dt. So that means we're trying to find dc dt, which means from our cost function we're going to be differentiating implicitly with x as a function of t. So derivative of 3000, 0, and this will be 20 dx dt. And so we plug in what we know. dc dt equals 20 times 10, which is 200. So dc dt is cost, so this is in dollars. So this would be $200 per home. So if you're looking at this and you're going, why is the cost so low? Well, remember, this is at the moment that they've already signed 400 people up. So in most cases in business, the more things you're producing or selling, the cheaper it is to actually make those or to do that, because you're already doing it such a large thing. Now there is a tipping point, right? We've been maximizing and minimizing functions for a few sections now. So don't think that that's always the case. More is not always better. But in general, if you're going to have to landscape, 50 houses, it's probably going to be cost effective for you to also landscape the other 50 that are on the other side of whatever neighborhood you're in. Okay. So part C, Doing the same thing once again, only now we're finding dp dt. So p of x equals r of x minus c of x. So dp dt would be dr dt minus dc dt. And we've already calculated those. That was 1000 dx dt minus 2x. 1000 dx dt minus 2x dx dt. And then this is minus dc dt, which was 20 dx dt. Now we've already calculated most of these things because this is nothing more than our dr dt value, and this is nothing more than our dc dt value. So dp dt would equal what we got up here, 2000 minus 200. Which is going to be 1800. And this is dollars per home. And so we can use the revenue and cost to make the profit a little bit easier to calculate. But that's related rates. So again, the hardest part is making sure you identify your stuff, your rates that you know, the rates you don't know, the variables you know, and then making sure you have the right equations. Now again, in this case, we had some custom equations that were given to us, so we knew which equations we were supposed to be using. And then the first example, we just were expected to know the area of the circle. And there's some of those that we need to know and don't know, but not many. We're going to be focusing primarily on cost, revenue, profit stuff. So this is a short one. That's the end of 3.9, and with it goes Chapter 3.